By 2050, the world is expected to be home to more than 10 billion people. Addressing the food challenges that accompany this growth demands innovation across the agriculture sector. Farmers are already feeling the effects of climate change as they seek to increase yields while they battle extreme weather events, accelerating crop disease, and price uncertainty. Finding data to help track and respond to these risks can be unreliable, expensive, and challenging to process into valuable insights at scale. Planet Monitoring for Agriculture is changing that. With our distributed network of satellites, Planet provides imagery of every acre on Earth, every day. Planet data is precise enough to discern field-level detail, ready to analyze for a range of applications, and delivered through a single scalable platform to provide insights everywhere your customers grow. Planet Monitoring for Agriculture. Data growers trust.
Good morning, ladies and gentlemen, and welcome to the Agritechnica Asia digital talk today. And we are talking today about new applications of daily satellite data for agriculture. And this is going together with the company of Planet, which I'm very proud of to have as guest today. Well, satellite pictures. In the 1960s, this technology started up, and with quite very coarse resolution of those imagery. Looking at those images from satellites of these days, I really wonder how anybody could read out anything out of that. So time passed, and nowadays we have a huge amount and a huge offer of satellite data, nearly frequently, nearly daily, and based on very different sensors or wavelengths which are detected. We're talking about visible detection, radar sensors are used, and also near infrared or infrared data are used. The questions, however, is how to use these data for agriculture. What is really possible? What is still a long way to go to have it really as a practical tool in agriculture? And most important, what is really already ready to use? My name is Klaus Erdle, and I'm from the German Agricultural Society, and I'm happy to answer these questions together with the speakers, with the guests I have here today. First one is Ariel Zajdband. He's project subject matter expert at the company of Planet. He has already held some impressive positions with other companies, however, all dealing on really one specific topic, which is the management of satellite data for agriculture. Ariel, I'm really looking forward to have you now for a first step into this topic. The stage is yours now.
Thank you so much. So I will proceed to share my screen. There. So thank you so much, everyone, for joining. And yeah, here I'm in California. I'm based in California. Here it's nighttime. Maybe you hear some kids in the background. My kids are trying to go to sleep, but I hope this is okay. Thank you again for coming. I prepared this presentation. The idea is basically to first talk a little bit about Planet, talk about some traditional use cases of Planet data, satellite data in agriculture, like what has been the most general use cases, and then talk about new applications. Basically, to talk about Planet, we like to talk about three main things that define what we do. The first one is our daily data that we believe that it's very important, in particular in agriculture, for regions of cloud coverage, where the likelihood of actually getting an image is much higher. We have actually very good resolution in terms of spatial resolution for agriculture that allows you to also monitor small scale farms, and we'll talk about that a little bit. And also our platform is easily scalable, and we have a global coverage. this video that I'm presenting here basically shows a little bit about planet, about what we do and the constellations that we have. That's the actual planet, and we have this constellation that we call Planetscope that is based on DAB satellites. They have a 3-meter resolution, and they are always on. And then we have the SkySat satellites that you need to go and task. This one have a higher resolution. They are actually 50 centimeters, and are typically used mostly for plantations and higher value crops. I'll keep moving here. One thing that I also want to mention is that we have a new constellation for Planetscope called SuperDABs. And as you can see here in the top, you have the Sentinel-2 bands, and then you have the DABs and the DAB Classic and DAB R, which are the typical Planetscope satellites that we have. And now we have a new version of these satellites, of Planetscope satellites, that are called SuperDABs, and they have actually 8 bands that, as you can see, are well aligned with Sentinel-2. Not only we have red, green, and blue, and near infrared, which is the typical one, but we also have the coastal blue, a second green, a yellow, and a red edge band that they have many applications in agriculture, and we'll talk more about that. In particular, the red edge band is particularly important for agriculture. And we've been also working on a product. Sorry, I'll stop here 1 second. We've been also working on this product for the last couple of years. That now it's been released, and this product is called Fusion. And as its name explains, basically what this product does is combines satellites like Sentinel, Landsat, MODIS, and all of the data that we collect at Planet to generate a daily image that is calibrated with Sentinel-2. Like you can see here, this video shows what you get when you get Fusion data. Like you get, even if you have clouds, you get 1 image every day. Maybe like just to not talk, like basically that's what I want to talk about Planet and the new products and the new features that we have in Planet. I'll also talk about the traditional use cases for satellite data in agriculture. Typically, satellite data in agriculture is used for three main use cases. The first one being is crop classification. Crop monitoring is a typical one, and the third one is the delineation of management zones, and also to create variable rate applications or prescriptions mostly in grain production. Before we go to the use cases, I want to talk about the importance of frequency. Planet has an almost daily coverage of the entire planet, and as you can see here in the graph in the left, this is particularly important. This is a paper that shows how basically the cloud coverage across the different seasons for different crops throughout the world. And you can see how in Southeast Asia, in India, and in some other parts of the world, such as Central Brazil, clouds are a real challenge in agriculture for crops like rice, like maize, soybeans, etc. So our customers really value that our frequency enables them to actually get more images throughout the season. But what we provide is not only a frequency, we also provide resolution. This is, in particular, this is a plantation in California, but you can see how going from a 30-meter resolution satellite like Landsat to a 10-meter resolution satellite with Sentinel, you can start, when you go from 30 to 10, you can start seeing more features in the landscape. But then when you move to a 3-meter resolution like the Planetscope data, you can actually capture much more features in that image. For crop classification, this is a typical use case used in agriculture. This is an example from Pakistan, where they were looking at tobacco crops in a province in Pakistan, and these were very small fields in very small farms, and they got a very good precision by using Planetscope. Crop monitoring is like the typical use case for using satellite in agriculture, and Right now, our data is powering very important platforms that are used globally, such as Granular, which is Corteva's digital platform. BASF's Xarvio platform also uses Planet data. And then we have platforms like Solimftech or Taranis, which are companies that are have a very strong presence in the US, but also in Latin America and globally. There are many use cases for crop monitoring, but one is, for example, looking at irrigation. And this is one example of crop monitoring, and it's very easy to detect crop failures in irrigation equipment by looking at satellite data. This is actually an aerial view of a field, and you can see these typical rings that show up when you have nozzles that are clogged or problems with pressure in pivot irrigation. So this is something that is very easy to detect with satellite, for example, and that the earlier you can catch these problems, the lower the yield losses that you'll have in the field. Now, if crop monitoring, zone delineation, and crop classification are typical and traditional use cases, I want to talk also about the new applications of satellite data, how actually having a higher frequency allows you to do things that otherwise are much more difficult to do. It's a long list. We'll go through it together, and I hope that that this is of your interest. And also, I'll be more than happy to answer any questions that you may have later during the Q&A session. Yield forecasting, we know it's key for not only for farmers to make market decisions, but also for food companies, for buyers, for grain buyers, for traders. We have many customers throughout the agricultural value chain that are interested in doing yield forecasts. And in particular, I want to bring this paper that was published. Actually, this is from Australia. Wheat in Australia, it's theoretical, but it shows how having a daily data of something called LAI or leaf area index, which actually with satellite we measure through an index called NDVI, usually in wheat, allows you to actually have a much better, much more precise yield forecast that also with a lower error. And this is not only because more data, it's just a better model. Also, more data allows you to, in this case, they show use different statistical tools to do these predictions. So this is a very interesting paper. If anyone is interested, I can share it with you. But this is the references here. In maybe a use case that is somewhat similar to this one is detecting planting dates, and actually this is also an experience coming from Australia, where typically people using satellites to detect planting dates, they rely on something that we call green update, which is when actually with satellites you can detect that there is a crop that has emerged, that there is a signal. And then typically what people do is that they subtract a fixed amount of dates from that green update. Now, that method has some error that it's usually 6 to 12 days, which, believe me, it's a significant error. And what this researcher did in Australia was actually just but having a daily data available, he was able to look at differences in the soil color and texture that were the result of the planter passing throughout the field. I have to say that this was these were no-till fields, and you can see how the prediction of that planting date was really good. Like in this case, the R-square is 0.99, which is like a dream for anyone doing any modeling with satellite data. We also have customers who are using our data and also other satellites to monitor sustainable practices. As we know, right now in agriculture, carbon sequestration is a hot topic. And more than carbon sequestration, I will call it reducing greenhouse gas emissions. And in particular, there are three practices that are typically mentioned, which are crop rotations, no-till or zero tillage, and cover cropping. And these three practices can be monitored and verified with satellite data. And something that is also very interesting, in my opinion, and that's why I want to share it with you, is not only to validate this practice, but also to understand and to help farmers manage this. So in this particular paper that I'm referencing here, what researchers did was looking at the cover crop that was planted before the cash crop. This is in southern Brazil, where farmers plant typically oats and rye before soybeans and corn. And they were looking at the biomass of the cover crop and basically delineating management zones for planting, so for fertilizer and variable rate seeding, based on the biomass of the cover crop that was planted before the cash crop. And that basically not only reduced the amount of data needed to generate the management zones, but also it gave farmers a much more accurate understanding of the water availability in the field at planting for that particular year, which is something that sometimes we miss when we create management zones that are based on the average of the last 5 years, let's say. I know that I might be very technical right now, but I believe that these are very interesting use cases, and again, happy to talk more about this in the Q&A or anytime, really. There is another practice that also is very relevant for reducing greenhouse gas emissions that I think it's also particularly relevant in Asia, which is basically dry seeding rice. We also have a lot of rice in California, not as much as you have in Asia, but we have a fair amount. And I took this example where with daily data, what you can do with daily satellite data, you can actually monitor the day where the fields are actually being flooded. And we know that delaying flooding dates reduces methane emissions from rice paddies. So definitely to the typical three practices, which are cover cropping, no-till, and crop rotations, I would love to add this fourth, which is the delaying the flooding date. Maybe I'm talking too much about carbon, and I like this meme because I feel that when we talk about sustainability in agriculture right now, we are only talking about carbon, and I think there is much more to that. And one of them is actually nitrogen. We now added 4 extra bands to our satellites, and one of these 4 extra bands is a band that is called red edge. Red edge is important for many things, but it's also very important when people are trying to calculate the nitrogen content of the tissue in the different crops in above ground biomass. And if you can actually measure independently above ground biomass and the nitrogen content, you can get what it's called the nitrogen dilution curve for different crops. And the curve here is the typical dilution curve, where as the crop grows, as you have more biomass, basically the amount of nitrogen, the concentration of nitrogen per unit of biomass is reduced because you have more structural tissue that typically has less nitrogen. So there is an index that was developed in France that is called the Nitrogen Nutrition Index that basically establishes a relationship of basically how sufficient is the crop in terms of nitrogen content. And we know that estimating crop nitrogen status also helps generating better fertilizer prescriptions, which at the end result in increasing nitrogen use efficiency. And we have this paper actually coming from Italy, where they were working in durum wheat. I just realized that I'm talking a lot about wheat. Wheat is a very important crop, wheat and rice. So I'm glad I'm talking about these crops. But in this particular paper, the author, she shows how the red edge band allowed her to separate the signal from biomass and nitrogen content, and to develop this basically develop this way of measuring the nitrogen content of the crops. And actually this idea of measuring the nitrogen content of above ground biomass, it's starting to be considered like a new paradigm in crop nutrition. This is a very complicated graph, but which is coming from this paper that was published this year in the European Journal of Agronomy. But if you stay with me, I'll try to explain this very briefly. The idea in the graph on the left is that we have this old paradigm where the fertilizer or the fertilizer rate is based on the amount of nutrients that we measure in the soil, and then we have these dose response curves, and then we fertilize based on these responses. But actually, we know that these responses are variable year to year based on mostly in the difference or the variability is based on the interaction between soil and weather, which is a season specific interaction that it's very hard to know beforehand. In contrast, what we are advocating now in agronomy is to actually do split applications where we are looking at the crop as the ultimate sensor of the nitrogen or any other nutrient status, and then splitting the application basically and basing the rate and the fertilization in general doing it based on what we see on the crop results also in a higher nutrient use efficiency, which is what we all want from an economic perspective and also from an environmental perspective. Another use case is verifying insurance claims. We have this picture here, which no one wants to see, which is like a crop that is destroyed by a weather event, and all this damage can be measured with satellite. We even have customers that are doing something called parametric insurance, where they don't have people going to the field to do the measurements, so that eliminates the need for paperwork, for gas, for people having to go to the field, and also instead of going to the field and measuring, basically sampling the field, you can measure the entire fields from your computer, right? So it's something that definitely reduces the cost of origination and policy adjustment. And I wanted to also include this picture because this was literally a day I was in South Africa, and we had, I'm originally from Argentina, by the way, that explains my heavy accent, but I was in South Africa, sorry, and we had a big hail, and then I went to a field with these folks to go and measure damage in a field, and you can see all the papers, and it took time, and I can tell you, like, the measurements that we took were very far from being very accurate. Also, I have to say, I had no idea what I was doing, but you can basically reduce a lot of the friction that is involved in insurance, in verifying insurance claims by using satellite data. Another use case that I wanted to also show you is around irrigation management, and not only detecting equipment failures like the one that I showed you earlier, but also it's becoming more common for farmers practicing irrigation to apply variable rate irrigation, to basically apply different amount of water throughout the field based on evapotranspiration and saltwater holding capacity. And our data that is basically measuring leaf area index, which is a proxy for biomass, helps you get a crop coefficient that is in the Monteith equation. Is like a very important component that allows you to also do this variable rate prescriptions. I've been talking mostly about agriculture, but in Argentina, agronomy is also animal production, and we have actually big customers in New Zealand, in Australia, in Latin America, who are using actually satellite data, daily satellite data, to measure forage availability on a daily basis, and they are making decisions about how to manage their herds, or how to manage their animals on a daily basis based on the data that they are getting from our satellites. And typically they are measuring just biomass, but we are also working with researchers who are starting to use our data and our new bands to model grass growth by looking at things like radiation use efficiency, by using the 2 green bands. I don't want to get very deep there, but there are ways of actually using satellites to measure that. And also to measure things that are quality parameters. So not only biomass per, like in tons, in dry tons per hectare, but also things like nitrogen content and digestibility, which can be also estimated with our satellites. And this is an example of a product that is based on our data. It's called Space. It was developed by the Livestock Improvement Corporation, which is a very large company in New Zealand. If you're interested, I think it's a very, very interesting use case of people making real-time decisions based on planet data. Another screenshot of their product that basically shows them the amount of biomass, as you can see here in kilograms, in this case, of dry matter per hectare. We also work in sugarcane with growers that are not only using planet data to go through, like, again, I don't want to repeat myself. I think that I'm already doing it, but it's also, they are also using planet data for harvest management. In sugarcane, for example, in Brazil, here in the southeast US, the sugar mills give daily quotas to growers, and they say, you know, you send me this many trucks, send me this many tons of sugarcane, and farmers, what they need to do is, on a daily basis, they need to convert from hectares, from area, which is what they manage, right? As a farmer, what you manage is an area, to tons, and they are using planet data to basically optimize their harvest planning. And we have stories where they, for example, used to some days finishing the day at 3 p.m. Another day they had to wait until 3 a.m. cutting sugarcane to actually fill the daily quota, to fulfill their daily quota. And actually now they were able to have a much more consistent operation based on the use of satellite data. That also, like, as you know, harvesting sugarcane is like, it takes many months. And I believe we are approaching kind of the end of the presentation, but I also like to show you how the other use cases that where a lot of companies are using planet data is actually monitoring field trials. I am an agronomist myself. Going to the field, sampling field trials is something that is needed, that people do. But sometimes companies are managing 40, 50 field trials in farmers' fields, where it's very difficult to access, where sometimes you don't get harvest data, so those experiments get lost sometimes. So what daily data allows you is, on one hand, to avoid destructive sampling and collect some, like, the entire plot data on a daily basis, to measure different phenotypic traits that might not even be visible to the naked eye, to avoid destructive sampling. And also, in some cases, like for example, seed treatments, the typical case, you have to wait until harvest to get the data on the efficacy of a given treatment, right? And in places like the US or entire regions where actually you can start gathering data earlier and then setting new experiments, maybe with fewer treatments, on a place where planting the planting might be like a month or 2 months later. That's extremely useful for these companies to basically their development cycles get accelerated by the use of daily data. And this is the last use case that I have, but I love this one, so you'll have to listen to me. Sometimes in production settings, like there is someone is distracted and they skip a row, or they actually do a double pass and they end up spraying twice. And these sometimes are what I call voluntary experiments that people do without thinking. And then you are curious, you want to know, well, what happened with that? what happened when we didn't spray? What happened when we sprayed twice? I'm not trying for people to spray twice, but I hope you can understand. So what you can do with satellite data is go back in time and use these experiences and as lessons, as opportunities to keep improving and doing continuous improvement on agronomic management. Of course, there are many more use cases in forestry, in plantations, in small-scale farmers, in the tropics, in temperate regions. I can talk about this for hours. Probably you don't want to listen to my accent for that long. But if you have any questions, feel free to reach out to me, to Jonathan, to Xinshen. They are based in Asia. We have people and we have offices in Asia. So and feel free to reach out if you have any questions. And also we'll be here for the Q&A. We also want to invite you to our we have basically a big event that we call Explore in 2021. Will be in October. So if you are interested, also feel free to reach out, and we'll have very interesting speakers to talk about different use cases too. So thank you so much.
Thank you, Ariel. And this was really an impressive presentation. And I already added at least one page of question I do have. And we have some participants who already put in some questions in the Q&A. So everybody is asked to add his questions to the Q&A. But this question we will address later on in the open discussion. So thank you very much. So I'm really curious about looking forward to the discussion later on. Maybe some of these questions will already be answered by our next speaker, Andrew Robson. He's professor and director of Applied Agricultural Remote Sensing Center at the University of New England. Andrew, you worked on a huge number of different crops using satellite data, sensor data. Maybe you can tell us a little bit more specific going into crop management, or what we can actually see out of data, of satellite data, and how maybe a farmer or a regional manager can use those data in his daily work. So Andrew, it's yours.
Thank you very much, sir. I'll just share my screen. Okay, can you see my screen okay? Everything okay? Okay.
Perfect, yeah.
Thank you very much. Thank you for the opportunity to present some of our applications today. So hello all the way from Australia. It's, what is it, 2:30 in the afternoon here. So yeah, I'm the director of the Applied Agricultural Remote Sensing Center out of the University of New England. We have a really good diverse group of scientists within our team from all around the world, all different experience, that together makes a really a good thought bank to build on what we do. So we do work across quite a few cropping systems, and there's a few of these listed here, and they range from sort of olive and citrus, mango and macadamia, rice and sugarcane, peanuts and avocado, pastures and bananas. There's a few more, but I think I'll start and limit to those. Because we're based in Australia, the majority of our research is done in Australia, and this gives you a distribution of all the sort of field work we do. So whilst the imagery side of it is essential for what we do an extensive amount of field work. So we try and encompass different varieties, locations, seasons, different managements to ensure that the remote sensing solutions are robust and repeatable. And I'll give you some demonstrations of those. So ourselves and our collaborators that we work with use a range of remote sensing technologies. So it's not about forcing a particular technology on a solution. It's more starting at what the problem is and then trialing the best technology and approaches to solve that. So we do use satellite extensively, and we use a lot of different satellite providers, most of the commercial ones. We do use airborne predominantly for thermal, looking at stresses and stresses in horticultural tree crops and irrigation efficiencies. We use drones to some extent, but more so our collaborating agencies use them more. In-field sensors of quality using NIR systems. We do quite a bit of hyperspectral ground-based calibration. We link with groups that do machine vision, and also we make sure that we integrate the remote sensing with on-ground sensors. So it's more of an integrated process rather than just the imagery alone. We definitely don't do this alone. We have a wide group of collaborators that we work with, and this is just a snapshot of them, the main point of this is that we work a lot with industry bodies. So they dictate the problem or the issue they would like addressed. We then, as we mentioned, bring a range of research agency and government agencies together to work on those issues. Obviously, the funders help, but we also work with commercial agencies as well to try and streamline some of those outcomes faster, I suppose, into the hands of growers. So for this presentation, I'm just going to give you a couple of one-page snapshots of applications that we do develop and have developed for a number of years in the centre. And this provides some context of how daily imagery may be beneficial or value add the stuff we're doing. I want to highlight 2 test cases, and one is our yield forecasting work in avocado, and also the national mapping of orchards. And I'll explain the relevance of that to this discussion when I get to it. And the next thing is how daily imagery can help these respective applications. So let's get into it. So one of the applications that we do with the World Bank, or have done with the World Bank in Uganda, was evaluating remote sensing, both high resolution satellite and field spectroscopy, for its ability to differentiate varieties. The main reason we did this was to try and understand the uptake or the dispersal of newly generated varieties through Uganda. So it was an interesting experiment, and we did get some positive results, which is ongoing. You'll notice that the blocks that we provide here, sorry, I should mention that Pre-Account Center was the main researcher out of our team on this. You'll notice from the breakdown of these slides, I'll give you these, I assume these presentations will be made available later, but I'll give you the application, the technologies, the different analytics we use. So we do use a range of analytics, including machine learning processes. So it's not all about machine learning. It is one facet that we use in the analysis. So keep that in mind, and some brief results. The next work I'd like to highlight is done by Dr. James Brinkoff out of the centre here. So Australia, this is for macadamia, estimating macadamia planting dates, and this across Australia and across different growing regions. Macadamia started in Australia, and so there's been a lot of orchards here for a long time. And so to help the industry bodies better understand when all the orchards were planted, James used a time series analysis of Landsat to go back and estimate when the planting dates of all the orchards are. And these are the 3 growing regions, Ballina, Bundaberg and Maxville. And this is sort of prediction accuracy he gets for the actual planting date. So this is all very important for yield forecasting, because obviously different age of tree dictates the yield potential of those trees. And leading on to yield, Dr. James Brinkoff also looked at establishing models for predicting yield at the block level. So he used a range of time series approaches using Landsat and Sentinel, and a range of meteorological data sets. He ran time series analysis for many years using historical imagery, as I mentioned, as well as historical yields achieved at these blocks. And that's another essential point for, I suppose, the success in what we do, is our integration with commercial growers across all these industries, and therefore access to historic data means that we can actually determine or establish some very strong models for all sorts of parameters. And this sort of gives you, that's these analytical processes used and the prediction accuracies. So not only is it a point prediction on tonnes per hectare, but also a derived yield map at the block level. The next one I'll show is sort of ramping it up a little bit to the tree level. So this is a combination of work initially done by Dr. Mashur Rahman, but more recent times by Dr. Priyakant Sinha here at the centre. So we're using extremely high resolution world view imagery to identify variability in orchards. We calibrate the spectral reflectance of each trees with yield produced, fruit size, and some other parameters. But we then extrapolate the information and derive yield maps at the tree level from satellite imagery. We're currently distributing these maps to industry using ArcGIS Online, and it's a very nice platform for getting it out because it's quite interactive, in which growers can click on each tree and get the tree crown area, as well as the yield forecast done by two different models. One by just using the reflectance of the trees, and the second using tree crown area by the reflectance of the trees. This year, we've rolled out about 300 mango orchards across 4 growing regions in Australia. Remember, if you want to look at any of this information later, there is reference to papers accompanying these slides. The rice one, so it was touched on by Ariel before. So in Australia, the application of nitrogen within the growing season is really important. So this is done at panicle initiation about mid-season. The problem is how much nitrogen to apply. If it's too much, the crops can fall over. If it's too little, they can suffer yield loss or loss yield potential. So again, this one's Dr. James Brinkoff again, has done some work in recent time with a number of different groups listed down here. And so he's evaluated a range of imagery sources, but the main idea was to develop a stable, robust methodology for delivering a uptake map or an application map for nitrogen over rice. The success of this process over the last sort of 4 to 5 years of research is that this year 10,000 hectares of these maps have been distributed to growers through the industry, the grower body Sunrise. So it's actually commercially getting put out there as well. The next one is sugarcane, and I'm not trying to repeat all the crops that Ariel spoke about, but we've been developing yield forecasting in sugarcane for over a decade. We've gone through lots of processes with remote sensing and tried lots of different methodologies and imagery. I won't go through them, but basically we're now, the best predictor is establishment of time series models using Landsat and Sentinel, where we actually go back over years of growth patterns for each growing region, and we work out, so basically it's planting, maximum growth, senescence and harvest, and then start again. We actually multiple stack these to form one quadratic equation for the forecasting of yield going forward. The accuracies are presented in various papers that you can find on our site, but as well as getting the forecast of yield, we also produce derived yield maps and crop vigor maps for all the regions. And at one stage, we're doing up to 100,000 crops every year. The next one, so a lot of those applications I've been speaking about are based on spectral reflectance properties. Texture is also a really important one, and that comes down very much to spatial resolution. So one group of work we did with a range of participants or collaborators, including the University of Queensland, Dr. Casper Johansson, who's now at KAUST, is to evaluate the potential of remote sensing for identifying damage from cane grubs. And the reason that's using a Geovia approach. By identifying where high risk or outbreak areas are, means that growers can apply control measures to stop the spread in the following seasons. So that was quite successful. The next one, or the last little subset example I'll give you, is the use, again, is crop classification, again, not trying to copy Ariel. So as well as the national mapping of orchards, James Brinkoff has been looking at the classification of 12 different crop types within a concentrated area of Australia called the Riverina. Again, he's used a range of imagery approaches and again, a number of image analytical processes. The accuracies of these forecasts are provided in this paper, so it is more than just a picture of it. There's actually accuracy matrix associated with that. So if you're interested, I suggest have a look at the paper. Okay, that's a quick snapshot of some of the applications. Two of the case studies that I'll do a couple of slides on. The first one is the work we've done on avocado. So this has been going for 7 years, trying to work out the robustness of remote sensing on avocado yield forecasting. So we have two main approaches, which due to time I won't go into heavily. However, what we do is we turn imagery into yield maps, so derived yield maps. So here, instead of just an NDVI image or a vegetation index, this is actually a kilograms per tree derived from satellite imagery. So obviously the benefits of this are directing growers where the yield variability is, and therefore we're through targeted agronomy, and therefore support the adoption of precision agricultural practices to identify wide limiting areas, et cetera, et cetera. We also derive fruit size. So the reason why we do this, so this is in grams size of individual fruit. derived from satellite imagery. So we're not counting the fruit. It's the relationship between canopy health and its ability to set and fill fruit. It's a physiological process that that's tied into this. So the benefit of having a yield fruit size map is that when a certain market dictates they want 200-gram fruits, rather than pickers going up and down every single row, they can actually target areas of the right size fruit, save labour, save time, ensure they meet the quota. So forecasting accuracies at the paddock level or at the orchard block level. Here's an example. This is 5 different orchards that were predicted using the satellite imagery approach. So the dark bars indicate what the actual yield measured from these crops were. The middle one was what our prediction was from our satellite imagery based approach. And the third one is actually the commercial practice. So this is how the growers estimate currently. The reason why this one, we've got lots of blocks and lots of years, the reason why this one's really nice is that you can see the discrepancies between actual and current grower estimate. Now this is extremely important. So if I grab out this block and have a look at it, the error in forecasting here, or the misprediction of forecast for this one block, based on an average fruit size of 180 grams and $1.80 farm gate price, is about a $1.5 million Australian discrepancy. So if you're working out labour, if you're working out whether the actual area is a sustainable area for growing avocado or not, I mean, this sort of level of inaccuracy is a concern. It is big dollars, and that's just one block. So we did develop a minimum viable product app for delivering imagery to growers and support this methodology. We hope to develop that into the full commercial platform in the next sort of 12 months. We're currently evaluating it with growers with the support of Hort Innovation, Australian funding agency, I should say. So it has the potential to take in daily imagery as well, or will have the potential to take in daily imagery, hence the relevance. Now, the next one I'll touch on is the national mapping of all orchards in Australia. Again, this, you might think, how does this relate to daily imagery? If you understand or know the location of every single crop, it greatly supports the automatic capturing of imagery, the processing, the applying of algorithms, and the dissemination. It greatly supports the scripting process of mass production of imagery. If you don't have that, then as you get imagery, you've got to sit there and delineate it. Now, there's a difference between accuracies of running a pure machine learning approach versus one where machine learning is integrated into the development of these maps. So, in our case, so this is freely available. There is a link that anyone can go and look in and go and zoom into. It has been developed with industry support. It is in industry data. So each of these industry bodies have provided historic data. It involves machine learning. It involves ground truthing. It involves apps to help consultants, etc., modify or adjust the accuracies. Oh, sorry, the borders. So it meets Australian standards. So I suggest you go and have a look. One good side benefit, again, of having a crop as well as the imagery, if there's a biosecurity outbreak, say here, you can quickly identify where the surrounding crops were, isolate an exclusion zone to stop moving, human movement, transport, and spreading diseases. That's some of the simplest ones. It also helps with natural disasters or weather events. So we've also integrated with the Bureau of Meteorology weather report. So the location of all the orchards is also matched with storm warnings and cyclone warnings, etc. Which means that in nearly real time, you can see when a storm's coming close to the orchards. Now, this is useful, obviously, for bananas, for example. If you've got enough notice, there's the opportunity to run harvesting 24 hours a day to ensure that the plants aren't knocked over. Also, it does help for the mass subsetting of blocks. So we had a cyclone come through Australia in 2017, which caused significant damage to cane crops and other tree crops. This is an area of all the different sugarcane crops in that region. This is the damage from the cyclone. Because we have also the ability to forecast yield from this imagery, we did a pre-cyclone forecast of the production of all these crops, and then following the cyclone. So not only could we quantify the area affected, but we could also change the forecast to allow the mills to know how much was coming in. So the benefits, again, this is sort of the linkage of that national mapping of commodities as well. There's a range of apps available on our website with bushfire and etc. Again, I encourage you to go and have a look. So the last little bit I was going to talk about is just how does daily imagery offer additional benefit to what we do and the applications I've spoken about. So the first one is I'll show one slide on how we've compared a number of different satellites together for mango forecasting. It also daily captures support the development of more sensitive time series algorithms. It offers greater frequency for irrigation and water stress, and Ariel again mentioned that as well. And it offers improved monitoring of crop planting and harvesting at the regional level. And again, Ariel mentioned that as well. So this one is a comparison of WorldView 3, Planet and Sentinel for the forecasting of mangoes at the orchard level. So here are 11 different orchards of mango. The first column is what the estimate from the grower is using commercial eyeball counting. The next one is what the actual yield were. So the yellow is actual yield. And the following three are the forecasts using the three satellites. So WorldView in orange, then Planet, and then Sentinel. You can also see the spatial structure of yield that we derived from these models. What's encouraging is the daily imagery provided by Planet provides the same spatial structure, and using our methodology is able to provide a competitive or a comparative prediction. There is a growers newsletter link here. This work was done by Dr. Priyakant Singh. I encourage you again to go and have a look. I haven't got much to go, so bear with me. The next one is, I mentioned the time series prediction for sugarcane. One issue with cloud-dominated areas and imagery such as Landsat, which is captured once a month, is that you can end up with large areas which are consistently obscured by a cloud. The ability to have daily imagery means that you can get around cloud a lot better, which means you can get a lot more point density on these time series models. The good thing about that is that you may better pick up little idiosyncrasies or changes associated with phenological growth stages, or little drivers of yield potential or yield change that may be occurring that you may in fact miss during this other process. So that's a benefit of daily imagery. Also for short duration crops like vegetables, and Dr. Angelica Suarez David from us, from our group, did a lot of work on carrots. They're only a 12-week crop. So if you're relying on weekly or monthly captured imagery, if there's cloud, you will miss the imagery. So daily imagery allows you to ensure that you get a good capture of these crops. Because they're small cropping areas rotated quickly, it also helps you identify those variations. It also potentially allows you to build short time series models based on that 12-week period, because you have daily captures. So that's really exciting. A huge benefit of daily imagery. The other one, and Ariel mentioned the irrigation. So we're running a massive irrigation trial on the biggest olive producers in Australia. So we're evaluating a range of technologies to see which one worked the best. And basically, daily imagery can help identify tree decline a lot earlier. It can identify issues with leaking or breaking irrigators. As Ariel mentioned, it can serve as a better input into a more sensitive input into climate-based irrigation models. But the other important thing is also, if you're using ground-based sensors to also record every 30 minutes, etc., the imagery is really important to make sure you put this sensor in the right place, and it gives you the ability to extrapolate the point source sensor measure to a greater region of the paddock. And the last slide I was going to show is that, again, this is an area of sugarcane production that we cover in part of our project. So I think there's 14,000 crops here. Daily imagery and delineating all the boundaries means you can rapidly produce these. You can identify the variation across the regions in terms of high performing and low performing crops, not just within the season, but across seasons, but also look at things like planting date, for rice when permanent water applications put on, and also harvesting progress. And you've got examples where, you know, blocks have been recently harvested because they've gone low in DBI because they're bare soil. That's a lot to take in. So thank you for listening. I hope it was useful. And if you have questions at the end, I'm more than happy to answer them. Thank you very much.
Thank you, Andrew. And this again was very impressive, especially the big gap between the farm estimate and your model estimate of yield. This is really a thing farmers really look on and then have actually a benefit out of using technology. Perfect. And using technology or using this technology in daily work of farming is also a topic Shijo Joseph is going into, because he's leading business and transformation digital initiatives at East-West Seed. And this means, Shijo, you build up the business behind the technology for the farmers. So I understand. And farmers are business guys themselves. So I'm curious to your presentation of how this can actually integrate it into farming business, these technologies. So stage is yours.
Thank you, Dr. Klaus. Let me share my screen. So most of the speakers before me spoke about various applications of satellite technologies. I'm aware of the time. I think I come from the application side of these technologies, being in the vegetable seed business. We at East-West Seed, we work with smallholder farmers. We take care of.
You may switch to the presentation mode. We see your working mode of the presentation. Yeah.
Is it okay?
Perfect. Yeah. Thanks.
So at East-West Seed, we work with smallholder farmers in improving their productivity by providing them quality vegetable seeds. And we are tropically focused and mostly in Southeast Asia. So when you look at the smallholder farmers, specifically in Southeast Asia, and we look at various digital technologies that we use, I think one of the key aspects is how viable these solutions are to the smallholder farmers. So that's one of the things that we keep in mind at most. And secondly, how specific can the technology and the solutions be to the farmers? Because most of the smallholder farmers work in 1 to 2 hectares of land. So it's very important that we provide very specific information to them. I think these are the two things that we keep in mind as a vegetable seed producing company when we look at solutions. So today I speak about two things very specifically where we use satellite data and digital technologies. One is, of course, enhancing the seed production. How can we enhance the seed production, both of our own producers who produce seed for us and also the farmer as well. Then I think the second one is more of a pilot phase for us, just to see how can the satellite information and digital technologies enable in go-to-market strategies. That's even if it's for sales or new products that we are introducing into the market, or even looking at new production areas for us to produce seeds. So these are the two topics I would like to touch upon today. So going to the use of satellite data and digital technologies when it comes to farming, I like to differentiate the farming into two. So we have customers, who use vegetable seeds from East-West Seed and who is using doing the farming for us. Then we also have growers or farmers, who we call, who are producers for us. They produce the vegetable seeds for us. So I think a lot of technologies we pilot among these vegetable growers who are associated with us, so that we understand the usability and the commercial viability of using these technologies, to the end farmers. So you can see these are things that we wanted to achieve, that there is an intelligence behind the decision-making process in a farm. We have a better understanding of what kind of pests and diseases and what kind of sprays, etc., should be used. Weather forecast is very important. And also irrigation is a very important aspect in terms of how do you control. So we put together all these things, as we call it, as a crop protocol. So we follow a crop protocol when in the farm in terms of farming. So that's completely digitized and automated. So what we are trying here is We are using a lot of ground sensors. So that's one aspect of the digital technology that we bring to understand a lot about the crop, about the soil and the weather, which is very specific to the farm. So we bring that information as one input. Then you have the satellite information. Then we combine these two, to create kind of a precision farming output, which goes as an input to the farmer at various stages. So this is the crop protocol management and farm level real data from the ground are things that we have already explored. And the satellite imagery are something that we are at this stage trying to combine and provide as an output to the farmers. And we are, of course, in the future looking at mobile imagery, and we are looking at drones and other aspects, of course, considering the size of the farm that we use, etc. So the output of this concept is basically, these are some outputs, that we can see from our current current concepts. So it gives you an overall understanding of how, the cost of the farming works, and it gives you satellite information on the temperature and all other aspects on the weather data. You can also see one of the key aspects. I said we are working with smallholder farmers, so it's not about using a very modern app all the time. So a lot of times a communication platform has to be, SMSs and very simplified messages over WhatsApp, etc. So you can see that here we have experimented with three kind of messages, and delivering those messages and information on time to the farmer is very important as well. So this is about the temperature. This is about the rain probabilities. This is about a disease prediction, which is using the AI algorithm and the data that we collected from the field. We are able to predict certain diseases and give an information to the farmer on time. So this is what we do today. Now, at the start of the presentation, I spoke, we are experimenting this with our own growers who are doing it, doing the farming for us, and we are seeing the commercial viability of it. And then we plan to extend this to the actual farmers. I saw a question in the Q&A session where people ask, how do you really convince a farmer to do all this? I think we took that route a while ago. I think the best thing here is to set up demo plots and really demonstrate the results. So some of the concepts that we are doing now is we are actually have set up a demo plot with all these technologies and monitoring capabilities adjacent to a traditional plot, so that we are able to showcase to the farmers the difference and the advantages of using these technologies. So I think that's the best way to convince them, because I think mostly for the smallholder farmers, it's all about seeing is believing, because they've been following a practice traditionally for many years. So it's not very easy to go and take a class or a lecture or conduct a meeting and explain to them about the benefits of this solution. The second possibility that I spoke about on using the satellite data and digital technologies is on the crop suitability. Traditionally, if you look at the Southeast Asian market, people are not very organized in terms of how they do the farming. Various things like crop protocols, crop rotations are not followed, very rigorously. So I think that's where we are trying to look at the historical crop health, the yield, and the historical data, try to combine it with the actual forecast and weather data and the cropping patterns, and to create a season outlook. That season outlook could be either for a product as a go-to-market strategy, or it could be even to identify the ideal areas for us to do seed production as we scale up our operations. So these are something that we have, we are at a very early stage. We are working with various partners to identify these possibilities. So those are some of the practical applications of using these technologies. As I said, it's very important that we keep in mind the commercial viabilities and the accuracy of the information and the timely delivery of this information, together with the platform that we use to deliver this information to the smallholder farmers. I think these aspects are very much important, and we keep that in mind while looking at all these technologies and its possibilities. That is it from my side. I'll open it up for the Q&A sessions where the rest of the panelists will join with me as well. But in case if you have any queries or anything, you can reach me on shijo.joseph@eastwestseed.com. Thank you so much, and back to you, Dr. Close.
Thank you. Perfect. Very shortly, and but just in time, perfect. So we have a good time to have an open discussion, which is actually necessary because we have a number of questions, and also I do have. So starting with the first one, so some go really a little bit in technical detail, and some are more on a higher level. So if we go, Shijo, you already talked about having the acceptance of farmers using the technology, which is the same in Western Europe. So there are a lot of providers of satellite technologies or using the technology, but farmers are not yet convinced. They did a few bad experiences in the last year. So, but technology is improving. So what actually, Ariel, there was one question to you. So there was somebody who had not the best experience on the reliability on the models in the past. So what did change in your technology? Did you fuse different sensors or data? So keywords like AI and so on. What did change, and what can we expect in future on that technology?
Yeah, thank you. Thank you for the question too. So something in the past that our customers have experienced is some inconsistencies among the different satellite versions that we have. That's basically why Fusion. So the Fusion product, the idea, and actually it actually works, and I would love to show you more of that, but the idea is to actually combine different sensors, and it's radiometrically, sorry, that's a difficult word for me, consistent and harmonized with Sentinel-2. Also, the new constellation of SuperDoves are also consistent with Sentinel-2, which is usually like the gold standard in remote sensing. And also we are publishing some coefficients to harmonize the data among our different satellites. So those are the three steps that we are taking from product, which is the unit where I work on Planet, to address this issue, which is fundamental when you are looking at time series data, which is like yield prediction, phenology, and many other models that Andrew was talking about that are fundamental because, as I mentioned, people don't want to look at images. People want to use this as a data source to then get an insight.
Okay, thank you. So it's a lot of using data of different sources. So Andrew, there was also a question to you, or this was also something I added on my list. Having a yield prediction of tree crops or other crops, or even, Ariel, you mentioned the nitrogen nutrition index. Is there a big difference on crop basis, and do you have to adapt your models also on the specific variety of the crop? So there's specific varieties, so especially in tree crops, leaves are differently shaped or have a different reflectance. How do you deal with these kinds of disturbances somehow? Maybe Andrew.
Yeah,
first.
Look, the first answer to that is extensive groundwork to compare and establish what those relationships are and how they affect remote sensing. Machine learning does not solve that problem. If you do not have the data to ground data to calibrate imagery and understand those relationships, you cannot correct for it. So that's my first comment about that. And in answer to your question, the second bit is, yes, there's a huge influence. There's a huge, as I mentioned before, there's a huge influence on season, location, variety, and management on every agricultural crop and every interaction with remote sensing. It's how much they vary and how you adjust for them in the methodology, in the forecasting, is how you solve it. That's my best answer for you. But the answer is yes, it's very, very difficult.
Okay, and do you then do a forecast is then really only done on this plot level because you know the environment of this plot or the field and the variety, and then you can do the forecast? Or going to the regional scale, you always have to adapt somehow to get a better predictions, no?
So when you talk plot scale, if you're talking research plots, they are totally unrelated to commercial production systems, and they do a total biased result, which is generally not transferable. So that's a huge limitation of a lot of research in the past, is not comparing the accuracies of these on commercial production areas. If you're talking a plot being an orchard or a paddock, look, it depends on the cropping system. Things like peanuts and sugarcane, you can get regional forecasting. That's quite accurate. Some of the works that I mentioned before that's been done on macadamias is getting good forecasting at the regional area. If you wanted to go down to the smallest scale, so whether it's a tree or whether it's a square meter or something, right down to that really fine scale, the safest bet is ground calibration of remote sense data, and that helps adjust for the variation in all these other parameters. That's the safest way. So,
okay.
Yeah, hope that
There's
answers.
still a lot of work to do. Even the satellites get out a lot of data, but the interpretation and getting out the real decision support for the farmers, still a lot of work to do. This is something some farmers do not understand. So, well, pictures are for free. What's the problem? Why is there any costs about that? So, yeah, that's a lot of work to do. So back to Shijo, that's actually your problem when you go to small-scale farmers. As far as I understood, your idea is to make, well, on a specific region, you adapt a model, you made example with mildew, as I understood as well, for vegetable. And then the farmers have the opportunity to go onto your platform or to use an app and get a recommendation for this specific region. And then they can decide on themselves if this is also applicable to their specific field, or in your case, small-scale farmer, or more to the small plot. But they have no real picture on their specific plot, but only on a representative you have, and they have then to go into their plot and do the decision then. Is it the right understanding I had?
That's right. I think we look at technology and how it matures over a period of time and how usable that information is. Till that point, we use it along with our own field representatives. So they are the people who are the first point of contact for the farmers. Then where we introduce the inputs and the outputs from these technologies to them. Then we pick up, the key farmers. We call them as a key farmers. That's what we are piloting now, where a farmer can independently use these technologies and, gain an ROI or a better ROI and an output. I think if we plan to if we achieve that, then we can go to kind of farming societies where these technologies can be deployed in a distributed manner, but at a much larger scale, so that it becomes commercially viable. So there are different models that needs to adopt. And that's how we look at it. And we see very typical challenges like, some of these technologies like ground sensing, etc., has to be very portable as well, because a smallholder farmer keeps changing his plot every year, because of the farming. So you cannot deploy certain things in the typical way or the fashion that we think about.
Thank you. Ariel, you had one example which was quite interesting for me. Dealing with a seed rate based on the biomass development of the pre-crop, so to say, on the cover crop before. This is quite easy to understand. You have a lot of biomass on the one hand side. You make a specific seeding rate and adapt it to a lower biomass rate on the other location. But what is the recommendation of Planet then? High biomass means I can do a higher seeding rate, because there is an argument between scientists sometimes, especially in Western Europe. So quite fertile soil, I do not have to seed that much, because plants can develop better on an individual basis, or I can even increase seeding rate, which means there's more nutrients and more water in the soil, so more plants can be supported. Is it the task for you to decide on that, or do you only offer the data and the farmer on his own has to decide what he's actually doing?
So that's a topic that I love to talk about, but I'll try to be brief.
Okay.
It's a common misconception that people say more productive soil, more seeds. That's not typically the case. Like in some crops like corn, that may be the case. In some crops like soybeans, it's actually the opposite. You might want to, like the recommendation typically is to actually reduce your seeding rate in more productive soils. Still, like more productive soils is a very big term. And this is also the case for fertilizers, where people say, well, in more productive areas, you might need more fertilizer. And that's not also necessarily the case, right? Because fertilizers, like the nutrients move. So yeah, again, like very interesting topic. But just to keep answering your question, we are not offer our product. Planet doesn't have a product that is proprietary that makes recommendations for farmers. We work with the industry and platforms that are actually using our data and converting that into insights for farmers. Sometimes we have farming operations that are using our data directly into software that gets into a prescription, but sometimes that gets into a model and the farmer doesn't even know that that's based on satellite data. So Planet doesn't have like an agronomic model. Planet provides satellite data to partners and customers that are working directly with farmers.
Okay, thank you. Again to you, Ariel. Planet is working mainly on satellite data. I worked on during my PhD time, I worked a lot with tractor-based sensors, optical sensors. This was, well, 20 years ago, something like that. There were no very frequently and high quality satellite data available at that time. So if a farmer has a tractor-based sensor, which also has a red edge inflection point or NDVI and so on, is it recommendable for him to anyway use satellite data as a surplus, or would you recommend, well, skip the tractor-based sensors, forget them, better use a Planet product, of course. But is there a big difference in the quality and in the outcome of the different sensors? Also, the principle of the sensors are quite similar. We have specific wavelengths. You can put in some specific filters to get the wavelengths. So on the farmers I talk with are still stay with tractor-based sensors because they say they had bad experiences because of cloudiness and so on, and not available data from satellite. So they stick to their tractor-based sensors. But what are the difference and what would be the advantages of satellite data at the moment?
I would say that like it's not about like competing with the sensors in equipment. I think that it's about complementarity. The sensors in the equipment, it's like having a scanner that you need to go through the field to gather the data. We are actually giving you the data before you get to the field and after you leave the field. So we are working together with companies equipment companies where the idea is not to replace the sensor data. Sometimes we provide a backup if the sensors fail, but also, and more importantly, in my opinion, to manage at a larger level. Like for example, saying, okay, where should the tractor go first? Like which field is ready to harvest now? Which field might be flooded, so you cannot enter to that field? And you don't need to enter the field to know that it's flooded, right? That's the whole point. So I would say that there is a lot of complementarity there, and we are working with some of the major equipment companies in the world based on this premise.
Thank you. Now a question, I don't know who would answer first. So big topic is also diseases. So having a satellite picture or satellite data of different sources, you see that there is something going on in the field. You may see already this difference between nutrient deficiency and a kind of disease, but is there a chance to also get out the information about the kind of disease? So really have the knowledge, okay, it's this kind of disease and now I have to, well, do any spraying or anything else. Is there the possibility? I still see some difficulties there. What's the technology offering at the moment on that topic?
I can offer some answer if you like.
Yeah.
We've done
Yeah.
a lot of work on diseases. I actually did my whole PhD on remote sensing for aflatoxin in peanut. We've done PhDs on Phytophthora in avocado, Panama, started Panama in bananas. Look, it comes down to the disease itself and what are the characteristics of that disease. So something that will prevent water uptake, thermal, for example, is a really nice way of looking at water stress because it's not taking up water. It also depends on the movement of the disease, the time it appears, what phenological growth stage it attacks. So this is where the importance of integrating the technology with knowledge, pathological knowledge of the disease is so important. You've got to remember that imagery is just a tool to assist in the interpretation. So yes, you can do it. And look, there's been a lot of push on hyperspectral as well in recent times. Look, hyperspectral works well for specific diseases under controlled conditions when there's nothing else affecting it. So if you have the same soils, the same water, same nutrition, and the only changing variable is the disease, yes, you can pick it up hyperspectrally. But under commercial growing conditions, that's not the case. You will have complications from nutrition, from drought, from other things that will overshadow the wavelengths you're looking at. So again, it's two things. It's understanding the disease with the pathology. Two, it's understanding the limitations and the possibilities of the remote sensing technologies. And the third one is just smart strategies on how you implement it. So I did a comment back to someone in the chat about the Panama. One of the biggest findings that we had out of that is 4 strategies to deploy remote sensing to make it work. So one is the detection, but you can't fly over every crop all the time trying to find the disease. You need to narrow down the when and the why and the what. So that's enough from me. I'll let the others answer.
Thank you. I expected that much. So unfortunately, I really have to look on the time, and I would have a huge list of questions. Actually, I and all the participants can contact you. We have your contact data. They can be looked up on the Agritechnica Asia platform, and you showed them yourself as well. So I will do so, and hopefully all the others as well. In the end, I really say there was a lot of progress in the last years on using satellite data. We have new satellites in the air, so to say, or in space, and we get really very valuable data very frequently on daily basis. We have new models, crop-specific, variety-specific, and we can look. So one topic would also have been the soil. I would really love to go in, but we have no time at the moment. So this is a big chance, especially Shijo told us also for smallholder farmers. So they should also be open to use these data. So the decision is, in the end, is on the farmer to use it or to make a decision on it. So, but trying out to test it and to help give the technology a chance to be used in practical farming is the first step to do for a farmer. In the end, it always is when harvesting, you really find out if it pays out in the end. And this is something we all work on. So technology will go on with AI and fusing different data. This will even improve. And I'm really impressed that we are already on this high stage of technological use of satellite data in agriculture. So thank you, Ariel. Thank you, Andrew and Shijo. And everybody is free to contact you, I say so, and me as well, I will do so. Thank you again, and thank you all participants here in the round to have these questions, and hopefully see you soon in live, in person, at the next Agritechnica Asia next year in May. Thank you again. Bye.